Alright, before we dive into the central limit theorem, we need to talk about the sampling distribution of the mean. The sampling distribution of the mean is obtained by taking many samples from a population, calculating the mean for each sample, and then plotting the frequencies of those means. And let me show you an example so you see exactly what I mean. Let's assume that we're interested in the daily rates for all the Airbnb listings in New York City at this point in time. Well, in that case, this would be our population of prices, which is close to 40,000 total. Now let's say that we take a sample of 5 prices from this population, calculate the mean, and then plot it in a histogram. And then we do the same for another sample, and another sample, and another, and we continue to do this, say, for 100 samples. Well, then the histogram on the right here is the sampling distribution of the mean. In other words, it's a distribution of the sample means from this population. Now, you might be thinking, well, that's great and all, but why should I care? And here's the mind-blowing part. The central limit theorem states that the means of large enough samples of any population will be normally distributed around the population mean. So if we look back at our Airbnb example, the population of the prices follows this distribution right here, which is clearly not normally distributed. It's apparent that it's not symmetrical around its mean of $172. But check this out. If I were to grab 100 samples of 50 random prices from this population and then plot the sampling distribution, then it would look something like this. Now this is normally distributed and around the mean of the population. And not only that, but the standard deviation, or the width of this distribution, is much lower than the width of the population distribution. So that's the power of the central limit theorem. Now to clarify, again, on the left here, we're looking at the frequencies of individual prices, or X values, which is what we've done in all the sections so far. But now on the right, we are looking at the frequencies for the sample means, which are represented by X bar, which you can see here. And another thing you'll notice is that I said large enough samples. And what I mean by that is that you'll typically want a sample size of at least 30 for the central limit theorem to apply. So if I had those same 100 samples of Airbnb prices, but with a sample size of 2, well then the sampling distribution would look like this. Not really normal, but if I increase it to 10, it would look like this. So starting to get a little closer to a normal distribution. And then by 30, it does look normally distributed, and even more so at 100. So key takeaway here, as sample size increases, then the sampling distribution approximates a normal distribution around its population mean. Alright, before I move on, I want to show you a quick demo in Excel that helps prove the central limit theorem visually. Now, I have added this as a resource to this lecture if you'd like, but there really is no need to follow along here, especially since I will be using a bunch of dynamic array formulas. Now, let me walk you through what we're looking at here. This is an array of 10,000 randomly generated numbers between 1 and 11. That's going to be our population, which makes our population mean 5.95 in this case, but if I go to refresh and generate a new population, you'll see that it'll stay oscillating right around 6, which makes sense because the randarray function generates random numbers from a uniform distribution. And if we look at the distribution of our population, we can confirm that with all the numbers having pretty much the same frequency. Key takeaway here though, this is not a normally distributed population. Now, let's say that we were to take 100 random samples of size 30 from this population. Well, we can simulate that in Excel. Let me use the sort by function first. And what I want to do is rearrange these random numbers randomly again so that I know that I'm taking a random sample. So I'm going to sort this array by a random array of the same size, so of the same number of rows. Again, no need to worry too much about the formula here. Just know that it's returning this same array, just ordered in a random way. So what I'm going to do then is just take the top 30 rows from this array. That's going to be my sample. We can see it here. And then just grab the average of these 30 numbers. Do the average. And we get 6.6 for our first sample. Let me just fix these so I can apply it down. Press enter. We get 5.7 now, which is plotted right here in our sampling distribution of the mean. And let's see what happens when I apply this down. And would you look at that, our sample means do follow a normal distribution around the mean of the population, which we know is 6. And if we were to calculate this now and generate more random populations and grab more random samples for those populations, we'll see that the same normal distribution around that mean continues to show up. So there you have it. Because of the central limit theorem, we can now assume that any large enough sample belongs to a normal distribution of sample means that is centered around the population mean. And we're going to be able to do some pretty amazing things with that. Alright, time for another highly important lecture within the context of this course on the standard error. Now, as you know by now, normal distributions are described by two values, their mean and their standard deviation. And we also just learned that, according to the central limit theorem, the means from large enough samples follow a normal distribution. So if we wanted to describe that normal distribution of the sample means, then the mean will be the same as its population's mean, but the standard deviation is different, and it's known as the standard error. So the standard error is just the standard deviation of the sample means around the population mean. And to calculate the standard error, you simply divide the standard deviation of the population by the square root of the sample size. And since the sample size is on the denominator here, well then as sample size increases, then the standard error decreases. Now, in our example of Airbnb prices in New York City, the population mean is 172 and the standard deviation is 144. So if we assume a sample size of 30 prices, then we divide 144, which is a population standard deviation, divided by the square root of 30, and get a standard error of 26.3. And what this does is that it lets us build this sampling distribution of the mean with a mean of 172 and a standard deviation of 26.3, which is our standard error. And keep in mind that we built this distribution just by using the mean and standard deviation of the population. Because of the central limit theorem, we don't need to go out and take a single sample to know that it will belong to this sampling distribution right here. And that's the big breakthrough. I'll go over all the implications in the next lecture, but I'll start with the first one right now. If you have data on a population, like we do here, then you can use its sampling distribution of the mean to calculate the probability of getting a sample of a certain size with a certain mean. So if we take a sample of 30 Airbnb prices, for example, it's very likely that their average price will be between $150 and $200, since there is a lot of area under the curve in that range here. But it's highly unlikely that it will be below 100, again if we go by the sampling distribution of the mean. Alright, time for part one of the payoff to this whole section, the implications of the central limit theorem. The central limit theorem has these four important implications. Number one, if you have data on a population, specifically its mean and standard deviation, then you can make inferences about any sufficiently large sample from that population. And this is the example that we just saw with the Airbnb prices. We have the population mean and standard deviation, so we can use them to build the sampling distribution of the mean, and then just use all of the normal distribution theory that we've learned to make inferences about any sample that we could potentially draw from that population. Number 2, if you have data on a population and a sufficiently large sample, then you can infer whether the sample belongs to that population. And this is very similar. You use the population data to build the sampling distribution, and then you see where the sample data lies along that distribution. And if the sample mean is improbably higher or lower than the population mean, well then chances are that sample is not from that population. Number 3, if you only have data on a sufficiently large sample, which is typically the case, you can still make inferences about the population from which that sample was drawn. So even if you don't have the data for the population, you know that if you take a large sample, then its mean will belong to a sampling distribution that is normally distributed around the population mean. So you can actually estimate it surprisingly accurately. And finally, number 4, if you have data on 2 sufficiently large samples, then you can infer whether they belong to the same population. In other words, if their population means are likely the same. And all of this is the basis for inferential statistics, which let you come to reasonable conclusions about an unknown population from a sample. And it's what we'll focus on for the rest of the course. So don't worry if these implications haven't fully stuck yet. As we apply them, then you'll start to realize how all of this ties together. Alright, so we just covered the implications of the central limit theorem. Time to turn them into applications. The central limit theorem has 2 key applications that we'll cover. Number 1, making estimates with confidence intervals. For example, you can use the mean and standard deviation from a sample to estimate a range where the population mean likely lies, which is exactly what we'll be doing in the next section of the course. And number 2, drawing conclusions with hypothesis tests. In this example, you can use the mean and standard deviation from a sample to conclude whether it was likely drawn from a theoretical population with a certain mean. And that doesn't seem like much now, but if we frame the theoretical populations correctly, then this can be a great tool for decision making under uncertainty. And finally, this can all be done using the same theory and Excel functions that we learned on the normal distribution in the last section, all thanks to the normal distribution of the sample means that our central limit theorem implies. So get ready to use the norm.s.dist and the norm.s.im functions pretty soon.